Today we're going to be exploring the graphs of polynomials. Now there are really two main ways to graph polynomials which we're going to use today and throughout this course. So the first one's a little more restrictive because it forces you to use the same procedure that we've been using this whole time in functions, which is to use the idea of translations and transformations in order to be able to graph something from a parent graph. So for example, you already know that if I give you x squared, right, this is x squared, you can graph any sort of transformation of x squared, and it's not too difficult, right? So for example, let's say I ask you to graph x plus 1 squared, let's do negative 3 times x plus 1 squared minus 2, for example, okay? So all you have to do is you have to flip it in the x-axis, so it'll first look like this, right? And then you have to give it a vertical stretch of 3, so we'll get like a point, negative 1, 1, negative 3, 1, negative 3, and you'll still have this parabola shape. And then these things tell you your translations, so you move 1 to the left and 2 down. So 1 to the left and 2 down. So it should be negative 1, negative 2. So here is negative 1, negative 2. And then I'm going to shift this point 1 and then 2 down. So that would be 0, negative 5. 0, negative 5. And then your final graph would look like the red, something like that. Okay? So you should be able to graph something like this using this type of transformation. Of course here, what we're doing is we're setting f of x equal to x squared. And this is just a transformation. This is the transformation negative 3 f of x plus 1 minus 2. Okay? What we are doing is we are taking the x plus 1, squaring it, and then applying these transformations afterward. Alright? So this should be mostly review. But of course, we don't have to stop with x squared. We can do this for any other polynomial, basic polynomial. So for example, let's go one level higher, which is x cubed. Now x cubed, you should know, looks like this. If you don't know, here you go. This is what it looks like, x cubed. Okay? You can check very simply, just by plugging it in, that there's a point here, 1, 1. Okay? Good to know, because that's what we're going to be using for our transformations. So now, for example, I can ask you to do, like, I don't know, x minus 2 cubed plus 3. Let's just do something with the thing on the inside. Let's divide it by 3. Okay? And then we'll put a negative out front. Okay? So of course the parent graph f of x is just x cubed, right? So what is this transformation doing? Okay, think about what this transformation is doing. So first of all, we need to get our equation into the form. Remember, the regular form is a times f of x minus c, sorry, there's a 1 over b up front here, plus d. So if we compare this and that, this is the same thing, right? So, sorry, maybe I can write it a little bit clearer as 1 over 3 times x minus 2 cubed, and you can check this is the same thing as that, right? And so we've got it into this form here, where f of x is equal to x cubed, okay? So that means we can just take this parent graph and apply our regular transformation. Okay? So let's do the stretching first. So here we have a horizontal stretch by 3, right? So that means this point 1, 1 is going to get stretched out to 1, 3. So maybe, I don't know, draw something like that. I'm just doing it very roughly. Of course, you can take this to whatever level of precision you feel comfortable with. Okay? So now we've got 1, 3. Oh, there's a negative here, so I have to flip it in the y-axis. So let's just go ahead and do that. I can just draw a symmetric image here. And then I'll delete sort of the old one. But what happened to our point 1, 3 is that it got reflected in the y-axis. So now this is actually the point negative sorry, no. That point up there was 3, 1, my bad. So if I reflect it in the y-axis, it'll actually become 3, negative 1. Brain fart, sorry. Sorry, I know you can't see that. Okay. So there we go. That's our reflected image. The only thing left to do is apply the translations. So, right 2, up 3. Okay. So what happens to this point? What happens to this point? Right 2 and up 3. Well, it should get sent to 5, 2. So we'll put 5, 2 somewhere here. 5, 2. And think about our point 0, 0. If we send it 2, 3, then it should be going to the point 2, 3. Okay. So that, I don't know, let's say it's somewhere here. So really we're just translating this up a little, and it should look like this at the end. Alright? And that's it. So that's pretty much how you tackle all of these transformation types of graphing problems. These are very rare, honestly, and the goal of the course is not to be able to do this, but you should be able to, just given the knowledge of transformations of functions, do this pretty simply. So I'm not going to dwell too much on this, but I think it's worth repeating what the polynomials, the standard polynomials look like, the parent functions, if you will. And again, as with all things with polynomials, they sort of split into two cases, even and odd, right? So typically what happens, we discovered last time that end behaviors are different, right? So we know that for even functions, the end behavior is infinity as x approaches infinity and as x approaches negative infinity. So eventually they'll go way up. Odd functions are kind of the opposite. They look like that, or they look like that. Okay. Here's a really nice tip. Even functions are even. Even polynomials are even functions. Even degree polys are even functions. So recall from the first unit that an even function is symmetric about the y-axis, whereas odd degree polys are odd functions, which means that if you reflect them once and then twice, they are the same thing. Okay? Or you can think about it as if you rotate it 180 degrees, it's the same thing. Okay? So just remember that from the first unit. Okay? So let me just, I think it's better if you do this on your own, because of course my graphing on the whiteboard is not going to trump Desmos. So actually go on Desmos and just draw out, x squared, x to the 4, x to the 6, and see if you notice a pattern. Similarly, graph x, x cubed, and x to the 5, and see if you notice a pattern. And what you should notice is that as you go forward through the series, you'll get like these weird things happening, right? So this is x to the 4, and x to the 6. Basically, it looks like they're getting very flat here. They're getting like flatter. I don't know the specifics, but it should look something like that. So x to the 6 is like super flat. Of course, x is our typical line, right? But x cubed looks like a cubic, so it looks something like that, right? And then x to the 5, it looks even more strange. It's like it gets very flat around 0, right? So this is like x to the 5. Okay. Of course, these are just diagrams. They're not really meant to accurately display what's going on. That's why I asked you to use Desmos, because I can't do it perfectly on the board right here. Okay. So I just want you to investigate this quickly. Just be able to know the difference, what a even degree polynomial looks like and an odd degree polynomial looks like. Okay. These are the parent functions: x squared, x to the 4, x to the 6, x cubed, x to the 5. Right? And I could be really evil and give you one that's like 7-degree polynomial, but it would just continue this trend of like still negative infinity here, positive infinity there, and gets very flat around 0. Okay. So there's really not too much to say about that beyond what I've just gone over. maybe it would be helpful if we went through one more example of graphing using transformations. Okay, this time we're going to use x to the 4. Okay, so f of x to the 4. And the transformation that I want to do is 3, let's do 3x, let's do 2x minus 1, all of that over, to the 4 plus 3. Okay, so remember here, f of x is equal to x to the 4, and we want our expression to be in the form a times f of 1 over b x minus c plus d. I always check this because sometimes, like in this case, you don't get something that's exactly in this form. And if you think, for example, that b happens to be like 1/2 or something, or maybe you think b is 2, that's an even bigger mistake. Then you're going to run into problems. Okay, so watch how I tackle this. So I need to get into this form. The only thing that could ever really cause problems is the b thing. So what you need to do basically is make sure that your x is totally separated into a factor that looks like this. So that means I need to take out this 2 somehow. I have to take it out from the 1 as well. So how am I going to do that? I have 2x minus 1, but this is the same thing as 2 times x minus 1/2. Okay? So all I'm doing is factoring out a 2 from both of these. Okay? To do that, I have to divide this by 2, and I have to divide this by 2. And that gives me this. And so I can rewrite my function as 2 times x minus 1/2 to the 4 plus 3. Okay? Alright, so just to remind you, our parent graph kind of looks like x squared, just maybe a little bit flatter. I'm not so picky on the detail here. As long as you show like the general shape, that's good enough for me. But you should be able to easily verify that the point 1, 1 is always on this graph. Okay? And that's because 1 to the power of 1 is always 1 to the power of anything is always 1. Okay, now to graph the transformation. So let's graph the transformation. We have to, so just be very careful here. This is not a horizontal stretch by 2. It's a horizontal compression by 2, right? So it's a horizontal compression by 2, which means this point 1, 1 is going to get sent 1 to the it's going to get sent half the way to the x-axis. So half of 1 is 1/2. So I have to put a point here. 1, 1/2. Sorry, it's the other way around. I'm mixing it up today a lot. 1/2 and 1. Okay, and then the rest of the graph just kind of goes like that. I think it's about time for a marker change, honestly. Yeah. Okay, so anyways, that's our point 1/2, 1. Then, if we apply the vertical stretch, notice how I always take care of the stretches first? That's because they tend to be the harder ones. The translations you can take care of at the very end, okay? It's typically the stretches that are the more difficult ones. So, if I stretch it up by 3, then this point 1/2, 1 is actually going to get sent to 1/2, 3. So let me just draw another graph up here. So it would look maybe something like that. And our point has got sent to 1/2, 3. Then the only thing left is for us to take care of our translations. So what are our translations? We need to get sent to, we need to move everything 1/2 to the right and up 3. So if we do that, where do our points get sent? Well, this point gets sent to 1, 6. So let's draw 1, 6 somewhere. That is not 1, 6. 1, 6. Okay. And what happens to another base point? I don't know. Let's choose 0, 0 because it's always easy. 1/2 and then 3. So its coordinate is going to be literally 1/2, 3. Sorry, 1/2, 3. Okay. And then you just draw the rest of it there. And that's about it. Notice I kind of drew it like a parabola. That's because it doesn't really matter. As long as you get the general shape, it's good enough. Okay. Polynomial sketching, in general, is just a very rough art. And that is going to be further exemplified in what we're doing right now. Because what we're going to do is move away from this technique and move on to a more useful and accurate form of graphing. even though the new form that I'm going to present to you may seem like it's even less accurate. Okay. So first what I'm going to do is I'm going to write a polynomial in factored form. What that means is that my polynomial, remember a polynomial looks like an x to the n plus an minus 1 x to the n minus 1. There's a bunch of terms, then you get a1 x plus a0, right? I can factor this. By factoring it, I might be able to get it into some form like ax minus 1, for example, or x minus 2, x plus 1, x minus 3, and so on. You know, I basically, everything is just multiplied together, and the terms all look like stuff like this. Okay? This is definitely possible. It doesn't always happen, but it happens for a lot of polynomials. So many polynomials, in fact, that it's actually usually a good idea to try and see if you can do this. The reason why is the following. And we actually touched on this last lecture, but I'm going to do it again. So maybe it's best if I just do it with an example. Suppose I have a polynomial f of x, and I already put it into factored form for you. It goes like this: x plus 1 times x minus 3 times, and let's say 2x plus 1. Okay? What I can do is use my knowledge about this polynomial in order to graph it pretty well. So firstly, the first thing you have to notice is that this is a degree 3 polynomial. In general, the number of x terms you see here is the degree of the polynomial, because when you multiply this whole thing out, you'll get x times 2x, and that's going to give you like 2x cubed. Okay? No other combination of terms will give you a higher power. Okay? So you should be able to check what the highest degree term is. If ever in doubt, just write it all out. Okay? However, that's pretty inefficient, and there is a much better way to go about it, which is what I just mentioned. Okay? Alright, so what I can do is I can figure out what the roots are. Remember, the moral of last lecture was that if I know the roots, then I can graph 90% of the polynomial. Right? So, two things. I know already that my polynomial looks like this. Okay? Actually, let's spice it up a bit. Let's put a negative in here. What the negative does is that, you know, if there's a negative out here, that means everything that I draw is going to eventually have to get flipped in the x-axis. So let's do that just to make it more interesting today. But we do the same procedure as we did last lecture. So last lecture what we did was that we set this thing equal to 0. If we set this thing equal to 0, this is asking for the roots of f of x. That's literally the definition of a root. F of x is equal to 0. So I set this thing equal to 0, and there are only 3 ways this thing could be equal to 0. Either this thing is equal to 0, this thing is equal to 0, or this thing is equal to 0. Okay? So if x plus 1 is equal to 0, then x is equal to negative 1. Similarly, I get as my roots x equal to 3 and x equals to negative 1/2. Let me draw those on the board. Negative 1/2, 3. Okay? And then I just have to use the other piece of information that I know is that cubics, so that's degree 3, they have at most, think about it to yourself, n minus 1 is 2. So 2 turning points. So that means my graph, the only way this could possibly work is if I do this, that, and that. And I'm done. It was that easy. Notice how this is so much less of a hassle than the transformation method. You can get it in one shot, just by doing a little bit of work on the side. Of course, you do have to figure out what the degree of the polynomial is. That sometimes is an issue, but for this case, it doesn't really. There's one last thing we have to do. Remember, we have to flip this whole thing in the x-axis. So that doesn't change the roots, right? If I reflect it in the x-axis, it's not going to change the roots. So all I have to do is just like draw a mirror image of this thing that I've drawn. Close enough. Okay? And that's f of x. We're done. Okay? So clearly, if I get my function into a factored form, this is particularly advantageous because I can do something like this. right? And this is pretty easy to do, right? Now, you may be hoping, can every polynomial be turned into something like this? Not quite. The reason why is because a lot of polynomials, not odd ones, but even ones especially, there are many situations where these polynomials don't have any roots. And you probably remember this just from quadratics, that if your function had no roots, it was a bit of a pain to graph. You had to figure out what this sort of vertex point was, and then you had to sort of had to maybe complete the square and then figure out how to graph this thing, and it was just messy. If you had the roots, if you had two roots, it was particularly easy because all you had to do was say, aha, root 1, root 2, and then I just draw my parabola. Okay, and at this point you can take care of the details after, but it was pretty simple. The same rule applies here. When our functions don't have any roots, they're harder to graph. So for example, if I gave you a quartic polynomial, remember a quartic is an even function, so as it goes to infinity and negative infinity, it's going to go way up, and it has 3 turning points at most. So 1, 2, 3. Okay. So here's an example of a quartic. It doesn't have any roots. Okay, this is a perfectly valid polynomial, but it doesn't have any roots. So this kind of thing is going to give us a lot of problems. Fortunately, the curriculum doesn't really force you to do a lot of these, and if they do, they make them easy enough so that you at least have an idea what to do. So that means our goal is to be able to graph polynomials using the factored form. Okay. All right. So I've done in the past 2 examples of odd functions. Let me do one with an even function. Okay. And this is the last example that I'm going to do before we actually talk about the real issue, which I'm going to bring up after this. Okay. So let f of x equal to negative 3x plus 1, x minus 2, x plus 3, x minus 4. Okay? Think about it to yourself. What degree is this polynomial? It's degree 4, because when I multiply these 4 terms together, that gives me the maximal power on x, which is 4. Right? 3x times x times x times x is just 3x to the 4. So it's going to be a degree 4 polynomial. The other thing I want you to notice is I did put a negative sign out here. Okay. Alright. So, what now? What now? We need to graph this thing. So remember, what we're going to do is we're going to first think about what the end behavior is. Now, the end behavior for a quartic polynomial is typically infinity, infinity. However, because of this negative sign, it's going to get reflected in the x-axis, so we get negative infinity, negative infinity. So we know eventually our function has to do this. I typically like to write these arrows. It just helps me. It helps remind me when I'm done getting all the roots. It helps sort of dictate the shape. Okay. All right. Next, what can we do? What can we do? Right, we need to solve for the roots, right? And I remember from last time, what did we have to do? Yeah, we had to set all of these things equal to 0. So let's do that. I want you to pause the video, come up with them yourself, and make sure all of our answers match. I'm going to write them on the side here. Okay, here's what I'm getting. So negative 1/3, 2, negative 3, 4. So let's put those in order. Negative 3 comes first, then negative 1/3. You can tell I'm not being super careful with these. It doesn't really matter. Okay, look, they're all evenly spaced out, even though these are completely different numbers. It doesn't matter. Okay, this is just a sketch. All right, and then what you have to do is connect it. We should write down here, because this is a degree 4 polynomial. How many turning points can it have at most? It must have at most 3 turning points. All right, TP at most. Right, so we should keep that in mind as we go here. So just like following through and just like, going 1, 2, you can do this. 1, 2, 3. Aha, look, that's it, right? Now I'm gonna edit this so that it doesn't look too bad. There we go. Okay, and this is a good enough sketch. All right? There's only one tiny detail that we can add to make our graph a tad bit better, and that is getting the point on the y-axis. Now this, it might sound like a really difficult thing to do. It's really not, because what is the point on the y-axis? That is just f of 0. We are asking what the value of this polynomial is when you plug in x equals 0. That's what this point is, right? This is x equals 0. So you just look at this and stick in a 0 wherever you see x. And this is pretty easy. You just get negative 1 times negative 2 times 3 times negative 4. You can do that, what is it, 8, 24, negative 24. So this is the point 0, negative 24, okay? It just adds one tiny extra detail to your function. Okay, so I think that should be pretty clear by now. Clearly, if I get my polynomial in this factored form, we are good to go. We are really good to go. The problem is, they're almost never in this factored form. You have to do the work to get it into that factored form. So now the question becomes, okay, so how do I turn a polynomial from its regular polynomial form to its factored form? That is a difficult question to answer, and it requires something called polynomial division. Now it has the word division in there, which should remind you of, like, you know, your regular division, and indeed they are the same thing. However, division with polynomials is, of course, a lot messier. Okay? And we're not going to do that right now. We're going to save that actually for next lecture, because it's a little bit of a difficult topic to cover. Alright, so instead of answering that question, instead of answering the question of how to turn a polynomial into its factored form, we're going to explore a little bit more about how this factored form can tell us more information about the graph, and what other kind of little inconsistencies we might get even if we do have our polynomial in a factored form. Okay. So the first thing that we're going to analyze is something called multiplicity. Okay, multiplicity. Okay. And to really understand this, what I want you to do is graph the following: x minus 1, x minus 1 squared, and then x minus 1 cubed. Okay? So if you do this, right, what you'll notice is that you get something like this. Okay? And it's a 0 at x equals 1. You do this one, right? You'll get a quadratic that intersects the x-axis, again at x equals 1. And if you do this one, you'll get a cubic that intersects the x-axis right here. Right? Now, I didn't need to ask you to graph these. You could have probably done them by yourself, just by what you know from translations and from graphing quadratics and linear functions. So this is just, I just asked you to graph it so that you would have it a little easier to see it. But what I want to analyze right now is what happens here, here, and here. Right? So what happened here was that your function just kind of like crossed it. Okay, so let's write here, crosses. It crosses the x-axis. Here, it bounces off the x-axis. And here, it snakes around the x-axis. So it still crosses it, but it does so in a way so that like it like snakes around it. It approaches, it becomes flatter, and then it leaves again. Okay? Speaking in the language of Unit 2, the instantaneous rate of change at that point is 0. Okay? So these are the three main types of multiplicities that we are going to be focused on. The reason why is because, say I have a function, f of x, and I express it in its factored form, but it looks something like this. Okay, it's not going to be the exact same thing as what we had in the first couple of cases. So these multiplicities, right, these powers up here, they can throw in some extra levels of detail, right? And those details are exactly what you see here. So whenever you have a root, right, we'll call these factors. Whenever you have a factor of multiplicity 1, it will always cross the x-axis at that root. Here, we have a factor of multiplicity 2. It will bounce off the x-axis at that point. And here, when we have a multiplicity of 3, it will snake around it at that point. Okay? So here is your general rule. Here's your general rule. There are 3 cases here. As you can guess, one of them is odd, one of them is even, but the other one is just when the multiplicity is equal to 1. So when you have multiplicity equal to 1, you just get a crossing point. Okay? So you'll get a cross. Your function crosses. And if all of this is not making too much sense right now, the next couple of examples I'm going to do will make it clearer. When you have an odd multiplicity, it will do a snake. And when you have an even multiplicity, it will bounce. Okay? So let's apply this to this function. Okay? So we're going to graph this function. Now, first thing I want to do is figure out what the degree of the function is. That's going to determine a lot of what I can do. Okay? So the degree, here we have x to the 3. Here we have x to the 2, and here we have x. So 3 plus 2 plus 1, that's 6. Basically, all I'm doing is I'm gathering all the terms that are going to have an x and then multiplying them all together, as if I were expanding out this entire thing. But to save myself a lot of the work, I'm going to only take care of x terms, right? So eventually, all you get that the degree is 6, okay? Which means that the number of turning points is at most max 5. Okay. Now, solving again for all the roots, we just do the exact same procedure as we did in the previous examples. We get 1, 3, and minus 2. Now, we have to take into account the end behavior and then the multiplicity. So this is a degree 6 polynomial. There's no negative sign out here. So what all that means is that we have to get the end behavior infinity, infinity. Okay, because it's an even degree, and there's no minus sign. Okay? In general, you want all of your factors to look like this. If I wrote my factors like negative x minus 2, then you would have to pull out a negative 1 from here. You want them to look like x minus something, okay? Or x plus something, okay? But never a negative in front of the x's, okay? You want to pull out all the negatives to the very front. Maybe I'll do an example of that after this, okay? So what we're going to do now is look at each of these and their multiplicities. So we know there's a root at x equals minus 2, but it has multiplicity 2. So that means here it actually bounces. So it should bounce off the x-axis. Next we have x minus 1. So this corresponds to x equals 1. Here it's a 1 multiplicity. So we get a cross. So this thing will have to cross the x-axis. And then here we have x minus 3 of multiplicity 3. This is odd. Therefore what we need to do is get a snaking pattern right there. And then just continue this off, and that's what your function should roughly look like. I want you to graph this on Desmos and make sure that you're happy with this. Okay? Now, just to count the turning points, we have 1, 2, 3, and that's it. You might say maybe that's a problem, but no, because remember, our turning points were maximum 5. That doesn't mean we need 5, that just means at most we can have 5. Okay? Yeah, I think that about does it for this example. Let's do some more. So I'm going to mix it up a little, throwing in the more complicated things from the previous examples. So let f of x equal x plus 4 to the 3 times negative x plus 2 squared negative x minus 1, 1 minus 3x squared. Okay? So, remember what I said. I need all my factors to be of the form something ax minus b. Okay? These ones are not of that form. So we're going to fix that. We're going to fix that by factoring. So in order to get a positive value in front of the x, I'm going to pull out a negative 1. So let's do that. If I pull out a negative 1, what happens it becomes negative 1. So remember, I want to keep the squared out. So it becomes negative 1 times x minus 2. Okay? Just to double check, if I distribute this negative 1 across, I get the exact same thing as I had here. So I haven't actually changed anything, right? Next, I'm going to use my law of exponents. AB squared is equal to the same thing as a squared b squared, right? So this thing is going to be equal to negative 1 squared times x minus 2 squared, where this is a, this is b, okay? But negative 1 squared is just 1, so we can get rid of that, and all we're left with is x minus 2 squared. So we can replace this entire thing here with just x minus 2 squared. Okay? Now, I want you to try this one and this one on your own. I'm going to rewrite them, and I want you to make sure that we get the same thing. Okay? Pause the video and try it on your own. So we should get here negative x plus 1, and we should get here, let's see, I'm okay with the 3. It's the negative that I'm not okay with. So firstly, I'm going to rewrite this, negative 3x plus 1 squared, and then I'm going to pull out a negative, okay? This is going to turn this thing into negative 1 times 3x minus 1. Distributing to double check, and it works. And then by the same argument that we had earlier, all we have to do is get 3x minus 1 squared. Okay? So at the end of the day, our function has really been reduced to the following. Negative x plus 4 to the cubed, x minus 2 squared, x plus 1, 3x minus 1 squared. The negative here I brought to the very front, just to be super clear so that we don't make any mistakes. Okay? And with that being said, we are ready now to graph this thing. Okay, let's go. Okay, now again, I want you to do some of the work. Try and solve all of these for 0 and figure out where our roots are going to be. You should be getting the following. Negative 4, negative 1, 1/3, and negative 2. 2. Okay? Now, I want you to try and find the degree. Again, pause the video, see if we get the same answer. 2, 3, 4, 5, 6, 7, 8. Okay. So if you're wondering how I did that really quickly, all I do is I take x, I look here, right? This really tells you the degree. So you go 1, 2, 3, 4, 5, 6, 7, 8. So the degree is 8. Degree being 8 means that we have at most, how many turning points? Should be easy by now, 7 turning points. Okay. Then the end behavior is infinity, infinity, because, oh wait, no, hold on. Usually it would be infinity, infinity. However, because we have the negative sign, we have to flip that completely. So negative infinity, negative infinity. Okay? Negative infinity, negative infinity. So I'm just going to put that there for reference. And now we're ready to graph. Okay? So what happens here, our first 0 is x plus 4. What happens here is that we need a snaking sort of pattern. So something like that. And then the next one is x minus 1. But x minus 1 is just has multiplicity 1. So we're going to cross. Okay? We're going to cross. And then what's the next one? This one, right? But this one is a even multiplicity. So we are going to do a bounce. And then this one here is the next 0. Sorry, this one. And it's also even. So we have to do another bounce. Let's do that. And that's our final answer. Let's count the turning points just to be sure that we didn't mess anything up. 1, 2, 3, 4, 5. Less than 7, it looks like we're good. Now again, I want you to graph this, make sure that we got it right. Okay? Make sure that you're really happy with this, because it's useless to be able to factor a polynomial if you don't know how to finish it off afterward. Okay? Yet another example. Let's pump up the difficulty a little bit. Let's make it a little bit trickier. Okay, I'm going to put something here that might fool you at first. So let's do negative 3x plus 2 to the 3, 5x minus 1, x plus 2, 2. Follow it up by, let's do, sorry, our functions need to have names. Okay, what did I want to do? Right, I like, yeah, x squared. Okay. Alright, so again, you know the drill. We need to first find the degree of the polynomial. And then max turning points you'll be able to get from that. And then I want you to figure out what the roots are. So figure out what the roots are. And you should notice something very strange happens. Okay, so let's go through and figure out the degree. Now the degree here is going to be 1, 2, 3, 4, 5, 6. This is an x squared, so 7, 8. Our degree is 8 again. Okay? And we have a negative sign out front, so that means our end behavior is going to be negative infinity, negative infinity. Usually it would be infinity, infinity, but because it's a negative, it's negative infinity, negative infinity. Okay? So our max turning points is automatically 7. Yeah, but our roots, you may have noticed something strange happens. Okay, so let's go through it systematically. This one gives you negative 2/3. This one gives you negative 2, which should be here. This one gives you 1/5. And this one doesn't give you anything. Because if you try to solve the equation x squared plus 1 for 0, you'll get x squared equals to negative 1, which means x is equal to plus or minus square root of negative 1. That literally doesn't make sense. Because this is an imaginary number, remember? We said this in the very first lecture. You can't take the square root of a negative number. So, what you have to do here is not do anything. Okay? If there is no root, don't invent one. Don't, please, 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 do not create a number here called square root of negative 1 and say, haha, I did it, I found the root. You don't. Okay? Alright, so be very careful about that one. That was a tricky one. Now let's see what happens. Okay? So, when we're graphing this one, actually no, the first one that we come across is this, and that's a root 2 multiplicity, so we are going to make a bounce. Boing. This one's a root 3, so we snake. And then this one is a cross, so let's do that. Cross. And then we're home free. We just keep going. Okay? Now I want you to make sure this looks something like the graph again. Now you'll notice this thing, there's probably some detail here that we missed. And it's pretty much always going to be because of this thing. Okay? Okay, so hopefully all of that makes sense. Maybe we can do one more example real quick. Yeah, let's do one more. This one will be very instructive because it will show you that sometimes, even though you think you may have gotten it in factored form, you might not. Okay? And it just goes to show how careful you need to be when you're doing these types of questions, because you miss one little thing and the whole thing crumbles. Okay? So, this one's going to look a little easier at first. Maybe not. Okay. So here's what we got. Yeah, I'm happy with it. All right. So if you try to went ahead and do this, let's see what would happen. Okay, what's the degree first? Okay. It's the same procedure you notice every single time, and that's what I want it to become. I want it just to become a procedure, but you have to understand why you're doing the procedure. Okay. So we have x squared. That's 1, 2. Now we have x squared, but to the third power. Okay, that's a headache. So hold on. We have x squared 3 times. That gives you x squared, x squared, x squared. So that's x to the 6. So we have 2 plus 6 plus 3. So 9, right? So our degree is 9, which means we're odd. It's an odd polynomial. Okay. No tricky negative sign out front. Nothing tricky here yet. So I think we can safely say that the end behavior is infinity, negative infinity, just like any other odd polynomial. Now, what do I want to do? Right, max turning points is 8. Eventually, you don't have to write this anymore. This is just a detail that I'm trying to show you for when you're beginning, but by the end of this unit, you should be like okay with this, that you don't even have to write any of this down for yourself. Like it should just be like really quick, like I'm doing it right now. Okay, now let's find the roots. 5x plus 3 is equal to 0. You solve that, you get negative 3 over 5. I don't know where that is. Let's put it here. Okay. This one you solve for 0, and hold on. That there should be alarm bells going off here because this is a difference of squares. That's a difference of squares. Okay, so hold on. Difference of squares. What was that again? So x squared minus 4, right, is equal to x plus 2 times x minus 2. But that what we have here is not x squared minus 4, it's x squared minus 4 cubed. So we'll have to make this cubed, and therefore this entire thing is cubed. By our laws of exponents, ab cubed is equal to a cubed b cubed. We have that this is equal to x plus 2 cubed times x minus 2 cubed. Okay, x plus 2 cubed times x minus 2 cubed. That gives me x plus 2 cubed, x minus 2 cubed. Oh, well, that's really strange. That's really strange because out of the one factor we got here, it sort of like made babies and became 2. So, okay, let's take care of that first. So we should have a 2 here, we should have a negative 2 here. All right, so that's concerning. And this one's a trap. It looks like you can't do anything with this at first, but if you pay attention really, really hard, 27 is actually 3 cubed. And this is not just anything, this is a sum of cubes. And we know how to factor a sum of cubes, right? If you remember the SOAP rule, this is the same thing as x plus 3 times x squared plus 3x, minus 3x, plus, I believe it's 9. Yeah, same, opposite, always positive. Okay? Alright, so that should be how you factor that sum of cubes. But then, look at this. This one right here is an extra factor, and it's only of multiplicity 1. So we've got like a bunch of roots coming out of nowhere here. So we've got to modify this a good deal. Okay, let me do it in purple just to get a different color up on the board. So we got negative infinity, positive infinity. Okay, now let's tackle all of these. So 5x. The first one's minus 3, right? This one cross. Well, by the way, this one up here you can try and factor it. You'll find out that it has no roots, so we don't have to worry about that one. Okay, so let's take these down one by one. The first one's a negative 3, and this one's a cross. So we're gonna cross. Sorry, where'd my purple go? Okay, cross. So it goes like that, and then at minus 2, that's this one. It's a snake, so we'll have to snake, but it's like a snake the other way. Something like that. I know I'm not the best artist, but it's okay. This is a even, so we bounce, and notice that even though I didn't want to, a turning point sort of has to be made there. Like there's no other way around it. Just go with the flow. So there's a bounce, and then what's the next one? Oh, it's x minus 2, right? So here what happens is a snake, right? And it's good because then it leads us right to the end. Okay? Now let's count the turning points just to make sure we didn't mess up. You can count it for yourself. I already know it's less than 8. We should be okay. Now, there might be some detail that we missed. If you graph this on Desmos, you may notice a couple of strange things that we might have missed. But the important part is that we got the main features of the graph, mainly the behavior at the roots and the correct number of turning points. Okay? So that's the emphasis of this lecture, just being able to graph from the factored form of a polynomial. We started off with some pretty simple examples, but as you can see, the examples can get pretty sophisticated, and they can break down into like these really complicated things. Right? So it's always important to be on the lookout for that, especially difference of squares, sum, and difference of cubes. Those are the two most common tricks that teachers will use on this unit in order to try and get you to forget to do things. Okay? So the more conscientious you are about these types of common errors, the less likely you are